Science tells us these incredible stories about our universe, right? From the smallest particle to the biggest galaxy. But how? How does it all work? Well, it all starts with something really fundamental: measurement. Today, we're going to pull back the curtain on the secret language that science uses to describe reality itself.
I mean, think about that for a second. It's a huge question, isn't it? If you wanted to describe everything that happens physically, you need a set of rules that everyone on the planet could agree on, like a universal blueprint for reality. So where would you even start?
Exactly. Before you can write the rules, you first have to agree on the language. And for science, that language had to be universal, it had to be precise, and it had to be consistent. But for a really long time, oh boy, it was anything but.
For ages, the world of science was, well, kind of messy. Imagine you're trying to build something with a team, but everyone's using a completely different ruler. That's pretty much what it was like. Just total measurement mayhem.
And here's a perfect snapshot of that chaos. You had some scientists using the CGS system, that's centimeters and grams. Others were on the British FPS system with feet and pounds. And then you had the MKS system with meters and kilograms. Trying to get everyone to collaborate was an absolute nightmare. Science desperately needed one single system to rule them all.
And so, that's exactly what happened. Out of all that confusion, this brilliant, unified system was born, so that scientists, no matter where they were, could finally speak the same language. It's officially called the Système International d'Unités. That's French for the International System of Units, but pretty much everyone just calls it SI for short. This is the global standard, the system that finally brought some much-needed order to the scientific world. Okay, so this new universal language, how complicated is it? Well, you might be surprised. The foundation for describing the entire physical world, everything we can measure, rests on just 7 base units. That's it, only 7. And here they are. These are the 7 foundational building blocks, kind of like the alphabet of our scientific language. The meter for length, the kilogram for mass, the second for time, and so on. Every other physical thing we can measure, speed, force, energy, you name it, is just a combination of these 7 core ideas. So, having the words, the units, is a huge step. But it's not enough. We also need grammar. We need rules that tell us about the quality of our measurements. Because let me tell you, in science, saying something is 5 meters long is very, very different from saying it's 5.00 meters long.
And this brings us to what I'm calling the grammar of measurement: significant figures. These are the rules of the road that add crucial meaning to our numbers and, most importantly, tell us how much confidence we can have in them.
Basically, significant figures, or sig figs as people call them, are all the digits in a measurement that you know for sure, plus one estimated digit at the end. So say your ruler shows 287.5 centimeters. You're certain about the 2, the 8, and the 7. That 0.5 is your best guess, right? That's your one uncertain digit. So that gives you 4 significant figures. And that number instantly tells another scientist exactly how precise your tool was.
Okay, the rules for counting them are pretty straightforward. First, any digit that isn't 0 is always significant. Easy enough. Second, any zeros that are sandwiched between non-zero digits, they're significant too. Third, any zeros at the very beginning of a number, like 0.00, those are just placeholders, so they're never significant. And lastly, this is the tricky one. Zeros at the end only count if there's a decimal point. That little dot signals that those zeros were actually measured and aren't just there to show scale.
And of course, when you start doing math with these numbers, there are rules for that too. When you multiply or divide, your final answer can't be more precise than your least precise measurement. So you just match the lowest number of sig figs. But when you're adding or subtracting, you look at the decimal places instead. Your answer should have the same number of decimal places as the number with the fewest. It's a subtle difference, but it's absolutely critical. Okay, so we've got our language and our grammar. But what about the sentences themselves, the actual equations of physics? Is there a way to, spell check an equation to make sure it's even logical before we go and spend millions of dollars building an experiment to test it? Oh, you bet there is. It's called dimensional analysis, and it's one of the most powerful and, frankly, elegant tools in all of science. You can think of it as the ultimate sanity check to make sure our physical descriptions of the universe are actually consistent.
So here's how it works. We completely ignore the numbers for a minute, and we just focus on the fundamental nature of the quantities, their dimensions. We represent length with a capital L in brackets, mass with an M, time with a T, and so on for all 7 of those base units we saw earlier.
This leads us to something called the principle of homogeneity. Now, that's a fancy name for a super simple idea. You can't add apples and oranges. In physics, that means you can't add a velocity to a force or subtract a temperature from an electric current. For an equation to be valid, every single term in it has to have the exact same dimensions.
Let's put this to the test with a classic equation you might remember from a high school physics class. This one describes the position of a moving object. We've got x for the final position, x0 for the starting position, v0 for initial velocity, t for time, and a for acceleration.
All right, let's break it down dimensionally. The final position x is a distance, so its dimension is length, or L. The initial position x0 is also a length, so that's L too. Now the third term, velocity, is length per time, so when we multiply that by time, boom, the t's cancel out, and we're left with just L. And the last term, acceleration, is length per time squared. We multiply that by time squared, and what happens? The t's cancel out again, leaving us with, you guessed it, L. Look at that. Every single term has the dimension of length. This equation checks out. It's dimensionally consistent.
So, why do we go through all this trouble? Why do we care so much about a universal language and this precise grammar and a consistency check? Well, because it's everything.
These are not just some arbitrary rules somebody made up. They are the absolute bedrock of modern scientific progress. The SI system, significant figures, dimensional analysis, they create this trusted framework that allows a scientist in Tokyo to confidently build on the work of a researcher in Toronto. It transforms what would be isolated observations into a global, collaborative story of discovery. So the next time you see a measurement or an equation, just remember the incredible system of language and grammar that's working behind the scenes. It's the silent scaffolding that lets us ask the biggest questions about our universe and actually have a shot at understanding the answers. It's the language we use to tell the story of the cosmos. So what story do you think we'll tell next?